So now moving forward, our next speaker is a principal specialist for quantum computing in the high performance computing group at Amazon Web Services. In this role, he leads a global business development team and goes to market activities for Amazon Bracket, a fully managed quantum computing service in the cloud. So everybody, let us welcome to the virtual stage, Mr. Michael Brett.
Hi, and thank you very much. It's wonderful to be with you today, and thank you to the organizers for this invitation to join you at this first quantum conference in the Philippines. I'm sorry I can't be there with you in person today. I would love to visit the Philippines sometime. Hopefully, we'll get the opportunity to do this sometime soon. So my name is Michael Brett. I'm based in Seattle in the United States. I'm originally from Australia. And my role is to help connect with customers wherever they are in the world and to help them get access to quantum computers through the cloud. And so what I have for you today is a presentation just to give you an overview of what Amazon is investing in quantum computing, to give you a sense of our motivations, the kind of technology that we're making available through the cloud today, how you can access this. If we get time during the presentation, I'll give a quick little demo. We'll see if we can do a live demo with a real quantum computer in the cloud and just show you just how easy it is to access quantum computing from wherever you are in the world. Whether you're in the Philippines today or your job takes you to new adventures elsewhere in the world, you should be able to access quantum computers anywhere in the world, and you can do that through the cloud. So we'll show you a little bit of what we're up to at Amazon. So to get started, I thought I'd share with you a quick origin story for Amazon itself. This is a diagram that Jeff Bezos drew on a napkin way back in the early 90s, thinking about the role that Amazon.com could play in building out a virtual store on the internet. And we call this the flywheel. And so what you see here is the virtuous cycle going on as the customer experience improves over time. So the better the customer experience is, the more traffic Amazon.com can get, the more traffic that we've got, the more sellers that we can bring onto the platform, which broadens the selection that's available. So more books available over time improves the customer experience. And then that helps grow the entire infrastructure of Amazon.com, which in turn lowers the cost infrastructure, leading to lower prices, which means a better customer experience. So lower prices with the best selection means the best customer experience, and then it's a virtuous cycle from there, and it grows and grows and grows and compounds on itself. And here we are 25 years later or so, and Amazon.com is as big as it is today, doing some really interesting things. And so this is the original foundational idea for why Amazon.com works the way that it does. How do we drive the lowest prices and the best selection and the best customer experience? Well, it's by operating this flywheel. And we do a very similar thing with quantum computing. So through the cloud today, we're also interested in the best possible customer experience, which leads to the best algorithms and applications, which allows us to invest in hardware, either building it ourselves or by working with partners. And then that in turn drives the best possible hardware quality to come into the cloud. And then as we grow, we can then do more customer engagement. That leads to better software solutions and tools, which leads to the best customer experience. So it's exactly the same flywheel concept. And if we've got the best hardware, the best software, and lowest prices and best selection for quantum computing, in exactly the same way as the original idea of selling books, that leads to the best possible customer experience over time. And so that gives you a sense of how we think about quantum computing at AWS. We are driven by delivering a good customer experience to you, and that customer experience, in turn, helps us fund growth, invest in hardware, invest in software along the way. And you'll see a little bit of that come through in the rest of my presentation. So what do we invest in? The pillars of activity at AWS and quantum computing fall into these four categories. So we have a service in the cloud called Amazon Bracket, where we make available quantum computers, and I'll talk mostly about that today. We also have a team that's focused on advanced solutions. This is essentially a consulting team that engages with end customers to do application studies, to do benchmarking, to do design and analysis, to work with the customers of AWS so that they can understand where quantum computing is headed, develop some intellectual property, benchmark and understand where quantum computing is headed. The third pillar is the AWS Center for Quantum Computing. This is where we build our own hardware, and I'll show you some photos of that hardware on the next slides. And then the fourth category is in post-quantum cryptography and quantum networking. And you learned a lot more about that with the previous presenter and the role of post-quantum crypto. But of course, here at AWS, we've got a responsibility to our customers to invest in that as well. And so we've got a lot of activity in post-quantum crypto, quantum networking, quantum communications going on. I'm going to mostly talk today about Amazon Bracket and a little bit about the AWS Center for Quantum Computing, but I'm of course happy to take any questions about the other pillars, and if we need to follow up, we can do that as well. So here's a look at our hardware center. So this building here is an AWS building. It's on campus at Caltech in Pasadena in California. So you can see the hills of Los Angeles out there behind. This is on campus at the California Institute of Technology, but the building itself is an AWS building. Everyone that works there is an AWS employee. We build and operate quantum computers in this facility. And here's one of my colleagues assembling one of those computers. We're taking a superconducting style approach to building quantum computers, which is similar to what IBM and Google and Rigetti and IQM are doing. We believe superconducting qubits have got some really interesting attributes that will allow us to scale to build up very quickly. And so here we are assembling a dilution refrigerator. Most of the equipment you see here is the cooling equipment. The chip itself, which is about the size of your thumbnail, sits in this gold chassis here. That chassis sits at the bottom of the dilution refrigerator. All this cabling, microwave control lines to control and interact with that qubit, with the qubits that are on board this particular chip. And so we're developing a whole range of different technologies to support this style of quantum computing. Something that we're focused on is introducing error correction techniques that would allow us to build a fault-tolerant quantum computer over time. And we released some news about this a couple of months ago based on a chip called Ocelot. Ocelot is a particular style of chip to test and to demonstrate some error correction technologies. And so if you want to learn more about what we're doing there, I encourage you to go read this article and learn a little bit more about the chips that we're building. Here's a closer look at the Ocelot chip, and this is the Nature paper that accompanied it, going through all of the technical detail about how we actually built that chip and tested it and the results that we got from the error correction there. We're not making these chips available to customers yet. We will do so in the fullness of time once those chips are ready. But for now, we're investing very heavily in the error correction technologies that will support large-scale quantum computing in the future. But for now, you can access a wide variety of different quantum computers through Amazon Bracket. So Bracket is a quantum computing service in the cloud. We've been running Bracket for almost exactly 5 years now. It was launched in August 2020. And Bracket is just like any other service on AWS, which means you can access CPUs, GPUs, a whole range of different accelerators and quantum computers through the cloud. And in doing so, we give you a choice of quantum hardware to work with, pay-as-you-go pricing, so you only pay for what you use. There's no upfront commitment. It's meant to be very easy to get started with, and then a consistent user experience across different quantum hardware systems. So Bracket really connects two sides of a market. We connect the quantum hardware providers, so third-party quantum computers, our own quantum hardware, with customer workloads today, which is mostly research and development, doing experiments for research and development purposes, but also learning and education and helping you prepare for future scale up, all within a consistent experience that's consistent as a cloud experience. It looks and feels just like any other compute in the cloud, but also consistent across a whole range of different hardware systems as well. So today on Bracket, we offer 8 different computers from 4 different providers. So from IonQ, Rigetti, IQM, and QEra. We've got a range of different systems from each. They've all got different properties. They've all got different attributes for how they do the computational work, and they represent different kinds of quantum computer. So you can experiment with ion trap computers, superconducting computers, neutral atom computers, and try out for yourself what makes these computers special and the performance differences between them. So it's a really great opportunity for any developers in the room today to get hands-on with real quantum computers, run real code on them, test for yourself how they operate, the kinds of algorithms that you can run, and think through the applications that could be made possible over time as well. If we get time in the presentation today, I'll give you a quick demo of the IQM system here. So let's see how we get through this. So just a quick look at how this builds up. So I'm going to show you now the stack that we work with. So at the bottom of the stack is the infrastructure we make available. We already saw the QPUs, the quantum processors, the 8 different computers we've got available. But we've also got simulators. We've got a whole range of GPUs and CPUs that you can run hybrid algorithms with. We can give different access modes, so you can access them on demand, run through different reservation cycles, and so on. On top of that is the software stack. So there's a software development kit written in Python. We've got local simulators, a whole bunch of different advanced features like pulse level control, hybrid jobs, access to third-party libraries, including the Qiskit library, Penny Lane, NVIDIA's CUDA-Q, are all integrated as part of AWS Quantum right from the outset. And then as developers, you can then build on top of that. You can build whatever you want. This is AWS. We give you access to the tools and the infrastructure to get building and to start learning. And you could access all of these today from your laptop sitting at the conference. Just log into your AWS account. You can access any of these computers and start learning. You can get advice from us. You can ask for executive briefings to your boss. And we can help you get started with quantum computing. That's all part of the overall service that we provide. So to give you a couple of ideas of where the Philippines could head with this, we work with a number of different national hubs around the world. So in Singapore, we work with A*STAR and the National Supercomputing Centre. In the UK, the National Quantum Computing Centre. Australia with Pawsey, and in Ireland, the National Quantum Cloud Environment. And we help these national hubs coordinate research activity across the entire country. So we work with the national hub as a single point of contact so that they can set up administrative controls and set budgets in the cloud, give them access to training and support, help them provide a single entry point to the cloud for everyone in that country to do research and development activity through a cloud environment. And I'd be delighted to be able to support researchers across the Philippines and across the region with access to quantum computing as well, if we can do something like that. So we can build on these examples and do something just for you as well. Another quick example of where we're helping out is through hackathons. So we just wrapped up the Southeast Asia Quantum Hackathon. Well, it's actually running this week. I've got one of my team is headed to Thailand to support that. We're working very closely with QBraid as a software provider that builds on top of Bracket. They connect their software environment through the Python SDK that runs on top of Bracket, and then accessing QPUs and simulators for this hackathon. Hackathons are extremely important for building out that community, giving us feedback from the developer community about what we need to improve on Bracket so that we can understand where this is headed in the future. So we're delighted to support that. Hopefully some of you are involved in this hackathon as well. One last quick example is with India. We've been supporting a program called the Mighty Quantum Computing Applications Lab since 2021. We've have an agreement with the government of India to provide up to $3 million in research credits, so offsetting the cost of compute in the cloud. So we cover the cost of the infrastructure, and researchers in India are able to access quantum computers through that. So far, we've delivered on 72 grants to 52 different institutions that's generating publications out of there. It'd be a great opportunity to do something like this in the Philippines as well, and be able to support research in your country. So that's another example of where we can work together in partnership and support research across the Philippines. So a couple of different ways to get started. We have a free online training pathway through AWS Skill Builder. So I'll drop the link into the chat. You can go online and run through some courseware that we've put together. It takes you through all of the training on Bracket so that you can run your own quantum circuits. There's a little quiz at the end, and you can earn a digital badge to put on LinkedIn if you like. We've got a whole bunch of different example notebooks and tutorials that you can work with. About 100 different notebooks on there. They're all free. They're part of the Bracket software development environment. And we can run workshops and immersion days. My team does training workshops and immersion days for corporate customers. Those are also at no cost. It's just a matter of getting in touch with us and helping to set up a date and bringing a group of people together. And we can take you through some hands-on labs in building out to help you learn how to build on Bracket. So here's my contact details. I'll drop these into the chat as part of the conference, but feel free to get in touch. My email is there, and I'm also available on LinkedIn. And I think I've got maybe 5 minutes before we get to Q&A, so we can do a live demo of a real quantum computer in the cloud. So why don't we do that? And I'll finish on that. So here I am logged into Amazon Bracket. I'm looking at the landing page for Bracket and through my AWS account. So this is just my regular AWS environment. You can access compute and storage and databases and AI tools and robotics and all sorts of cool stuff. One of the services available through that is Bracket. And so if we go to the dashboard, all of you would see this exact same environment if you logged into AWS today and access Bracket. So there's various announcements. You can access community support, different resources for getting started, including the learning plan that I mentioned before. This is our free online self-paced training. There's a developer guide. And then if you go to the devices page here, you can see the status of all the simulators and the quantum hardware we've got available. So there's 3 different simulators at the top. Hardware available from IonQ, IQM, QERA, and Rigetti. If you click on any one of these pages, it'll take you to more information about this particular machine. It shows you its availability cycle, the pricing. You can get a sense of the calibration and the layout that's available. There's a lot of information here about each of the different computers that you can access through the cloud. If we look at IonQ, you can see that the layout here is very, very different. These are different devices that have got different techniques. Here we've got the notebooks environment. These are all the free example notebooks that are available. And I'm about to switch into one right now. And we're going to take a look at running a quantum circuit on a QPU device. And we'll step through the code here really quick and show you what it looks like to run something on a real quantum computer. So I'm going to click through the code. What we're doing here is we're importing the libraries that we need. So we're saying, hey, program, bring in the Bracket SDK, bring in some plotting libraries and a few other things that we need to support that. And then we're going to ask it for all the gates that we've got available on this particular device. So we've said, hey, computer, what can I run on you? What gates do I have available to work with? And it's saying that in the SDK, we've got all of these gates. And then on the IQM device, we've got a subset of those gates available to us, including CNOT gates and so on, if you program quantum computers. And then we're going to set up this circuit. So what we've got here is 2 qubits. So we've got the qubits of the horizontal lines. We've got a Hadamard gate and a CNOT gate. Together, that creates something called a bell pair. And so we're going to define that particular circuit. We're then going to send that circuit to our local simulator and we're going to do 1,000 shots on that local simulator. So, oops, what happened there? Let's try that again. Let's go to the top. So we're going to do 1,000 shots on that simulator, which is essentially flipping 2 coins 1,000 times and getting the results from that. And what we've got is, because these states are entangled, we flipped 2 coins 1,000 times, and we got heads, heads, and tails, tails every single time out of there. And we got no instances of heads, tails together. So you would expect that we'd get 25% of heads, tails, and 25% of tails, heads, but we didn't, because these are entangled states. And so we always got heads, heads, and we always got tails, tails. Now we're going to run exactly the same experiment, but on real hardware this time. So we're going to send it to the IQM quantum computer. We'll just do 100 shots on here. And that's what we did. So we just sent it to the IQM computer. It's saying that it's currently queued up. And so if we go back to this page and we look at the IQM machine, you can see that oops, we'll forget that for now. Let's see where we are in the queue and see if it's been completed. Great. So it says it's been completed. It's run on a real quantum hardware. And now we're going to look at the results that we got from that. Here we go, plotting the chart here. So we ran 100 flips of 2 coins. We got heads, heads, and tails, tails. But we also got some tails, heads, and heads, tails, because these are noisy systems. This is a noisy quantum computer. And some errors creeped in, which is what we expect on these very, very early stage devices. And we got some randomness coming into our entangled state. And so this shows us that we worked on a real quantum computer. We got results that were affected by noise, which means we, in the long term, need to build fault-tolerant quantum computers and introduce some error correction to correct for these errors that crept in. But we got a result that shows us that real quantum hardware is working in the background that broadly matches the simulation result, but with some noise that's added to that. And so what I just showed you was a real run on a real quantum computer in real time as part of this. And you can do exactly the same thing once you get back to your desk and start playing around with this and getting access to real hardware. So I'll finish up there, and I'm more than happy to take any questions you have.
All right, thank you so much, Mr. Brent. So the floor is open for questions. Anyone? Yes, we have one question right there. Yeah, go ahead.
Hello. Okay, so Aria from Thailand. I'm actually one of the organizers of the C hackathon that you mentioned. So thank you so much, AWS, for being the supporter for the event. So I have this question that I never got an answer for. So you mentioned that the platform, the bracket, can access to many multiple devices, right? Including the from AWS. So like how does the cost and the queuing thing worked with this thing? Because I know that using the QISTCon and the IBM machine, there's a lot of complications going on with like queuing and waiting, and then the cost that takes from there. Like how do you manage with a lot of devices?
Yeah, sure. It's a good question. So queuing, we handle queuing on the AWS side. And so when a user submits a task, like what I just did, it goes into a queue. Sometimes there'll be lots of tasks that get batched up, but it is first in, first processed. So if you submit a task, you just stay at the front of the queue, and well, you are in the queue until you get to the front, and then you get processed. So we don't prioritize any traffic. It's very democratic. If it's a busy day, you might just have to wait. If it's not busy, then it's easy to get on, and that's what you saw in the demo that I just gave now. That it happened to be no tasks were queued up on IQM, so we were able to do it in real time. Sometimes we can't do that because it's busy.
Right.
We
But
also,
yeah.
yep. And then on pricing, so we price based on tasks and shots. So when you send one algorithm to any of the quantum computers, it's 30 cents to process that algorithm on the quantum computer. If you need to loop through that same algorithm many, many times, so you're doing machine learning or you're VQE and you need to converge on an answer and loop through, say, 1,000 times, we call that a shot because you're looping through the same circuit. And the shot price is very small, but it can add up because you're looping through many times over. So it's shots and tasks. So you only pay based on the consumption of the compute that you used. So it's 30 cents on every computer for the task, and then a slightly different price for the shot on each system.
I see.
The Bell circuit that I just ran on that IQM machine, that probably cost 32 cents to run.
Right. But then like in the sense, when we submit a job, we need to specify which device we want, right? Like, hey,
that's
can
right.
you do something more like, oh, I want any device that is available now.
Yeah, that's something that we might introduce in the future.
I see.
A feature where we select on your behalf the device that's best suited to run that particular algorithm, but it's not something that we currently have. So right now, you as the user need to specify which device that you want to target, and that's a choice for you. But I can see us introducing some feature in the future that does that automatically on your behalf, but we don't have it yet.
I see. Thank you very much.
Thank you so much for that wonderful question. Any more questions from the audience? Anyone anyone in the Zoom meeting? None? Oh, okay. Hi, Mr. Brett. Brett, I have a question. So, do you offer any kind of reservation on uh, on a particular computer? Let's say
Yeah,
25% of the Q era computer.
yeah, we do. So we offer two different modes of compute. So we've got the on-demand mode, which is what I've been talking about so far today. But if you get in touch with us and say, I need a reservation next Tuesday for 3 hours because I've got a big experiment that I need to run. It's a hero run and I need to collect all of the data and I need exclusive access to that particular device for 3 hours next Tuesday. We can do a reservation that gives you that exclusivity in advance. And that's a conversation that we have together to make sure that you're getting the access to the right machine. We do some verification with you to make sure it's going to run in the right amount of time. And there's a different price for the reservation window through that. It's not that common that we do that. We'll do a couple a month of that, of reservations. And it's typically for users that have been doing a lot of research on the machines in an on-demand capacity, and then they want to do something like really big to collect the final data set for their project.
All right. Sounds great. Thank you so much, Mr. Brett. So I think that ends our Q&A for Mr. Brett's presentation. Thank you so much. And I'll give back the floor to the masters of the ceremony.